Today, I had the privilege yet again to speak with Scott Walter, who is an offline programming pioneer, co-founder of Deneb Robotics in 1985, and also co-founder of Visual Components in 1999, where he is the chief technical advisor. Today, Scott and I talked about Optimus, and we got so deep into it that I decided we had to break this whole thing into two pieces. So watch this episode, definitely subscribe, and catch the next one when it comes out. In this first part, Scott gives a whole bunch of background about robotics, about kinematics, about how robotics actually works in the real world and the virtual world, and why simulation is so important, and also why Optimus is going to suck at soccer. Let's take a look. Hey y'all, it's Dr. Know-It-All. So I have the privilege yet again of speaking with Scott Walter. This is one that we talked about several weeks ago, actually, and we're both very excited about that. And that is diving deep into Optimus, the Teslabot that Tesla has talked about, and getting a sense of what it might look like and how it might act and the sort of physical limitations on a humanoid robot. So yeah, I'm super excited to talk. Scott, I don't know if you want to show your shirt. We have our shirts, you know, because we
we got a t-shirt theme going on here. So
yeah.
So this one is simulating since 1999. We've got kind of the human model on here that we start to simulate in there. This is we get these t-shirts when the company turned 20 years old.
There you go. So yeah, so a lot of what you do is simulation, and so that's great because it's a fantastic thing to do. Obviously, before you build a robot, is to simulate the robot. And of course, I've got success as one of the possible outcomes. Elon Musk quote, which seems to be reasonable, and of course, my Teslabot.
Yep, the Teslabot.
People can get that stuff in the, if you check out the link in the description, you can get those items if you're interested. So anyway, yeah, so I think, I don't know, let's maybe show us Teslabot for people who haven't seen it recently, and then we can sort of backfill and get to what we're gonna do. More than likely, this video is gonna be broken into two just to let people know, so definitely subscribe so you can catch both of them. All right.
Okay, so what do we know about the Teslabot? Well, actually, we don't know a whole lot. And the reason we don't know a whole lot is not a whole lot of details that come out. This is one of the slides from AI Day. There were a couple of other slides from AI Day, but this is the one that I got excited about. I mean, everything else about the Teslabot, there were a few other things. And we're going to go into the technical details in a lot of detail. But before we do that, we're going to have to lay some foundation.
Right. And just for reference, this would have been August, what was it, 21st, 19th, something like that. It was about 11 months ago now.
I just remember this being last year.
Right. It was 2021.
Last summer sometime. Yeah. Last summer sometime. Yes. And so we have a little bit of a plan what we're going to go through here. And so it's going to be a couple of chapters where we're going to sort of look at the Teslabot and a little bit of the background from the AI Day slide. And we're more or less, it's probably going to be more towards the end than the beginning, but we'll discuss it a little bit. And the next thing is we just want to look at some examples of workers in factories. So we understand what is it that they want the Teslabot to do. So that, the focus is to help manufacturing at Tesla. So what do they typically do, or what happens in other ones? We'll also do a little bit of kinematics primer, which I think you'll find kind of interesting. That we'll try not to get too much into deep, heavy math or anything like that, but just enough. Everyone should be able to do it.
This is like one of my favorite things because, of course, I teach 3D animation, which involves an awful lot of kinematics. So there you go.
Exactly. And then the other thing we're going to do is we're going to look at some other examples of some humanoid robots that are out there. Most recently, the one from Giant AI. And the video that kind of goes with it. And the reason we do that is, you can learn something, not so much from what something is, but what it is not. So the best way for us to understand what the Tesla robot's going to be like is to kind of figure out, well, we know it's not this, so it may be something else. And there'll be some very good things for us to be able to compare and contrast.
Cool. And I'm going to do a little plug for a previous video, the examples of workers in factories. I'll put a link to that up above because that it's actually a very popular video. The two of us discussing like the factory, the structural battery pack and getting into factories and ergonomics and stuff. So yeah.
Yep, go ahead and plug that one.
Yeah.
And then we'll also kind of look at how you would use VR to teach human robots in ways that's being done. Okay, so we'll start right into it. Here's the technical details for the Teslabot. And we could see it's only going to be about 5'8", so it's going to be shorter than me. And they're talking about having human level hands, which is rather interesting detail. Not a whole lot is going on there, but it's over here that I found this really interesting, and we'll deep dive into these numbers. So the first thing I thought about is like, oh, I wonder how many servos they have, so I have an idea of how many joints they're using in their overall model. Now, when I started to analyze it, the first impressions I had was this: is that we all know Elon's mantra about prototypes. And in this case, I feel the prototype is hard, the production is easy. Well, once they get the prototype down, producing this thing is going to be fairly straightforward and easy. Unless there's some like really super complicated servo that they had to invent, it's just difficult to mass produce, but I really don't think so. And the two main challenges, I think, is going to be a good hand, and B, the general AI that's going to go along with it. Okay. So, trying to solve both those problems at the same time. Everything else about these robots is pretty much a solved problem, except a really, really good hand. Okay. They're getting better, but the way a human hand works and the dexterity that's there is really something else compared to what we've been.
So you just for reference, because I've seen like Boston Dynamics and stuff, and they have those giant backpacks on those things.
Yeah.
You don't think like energy and compute power are going to be? I guess the compute power relates to the AI ability.
Yeah, I think part of it is if you're putting something out in the field, you're never near a charging station, right? Right. If you're in a factory, you probably have a lot more. The other thing is that running takes a lot of energy.
Right.
Compared to walking. So long as this isn't running the whole time, you can probably go a lot further. I mean, we know that with your Tesla, is like you're driving around, if you decide to accelerate a lot and go really fast with a lot, you can really see the percentage go down really fast. So
right. And I think Elon said that they've limited at least the last AI day, it was like 4 miles an hour, 3 miles an hour, something where if you
can run away from
rapidly, you could run away from it.
Yeah. 4 miles per hour is a very brisk walk.
But anyway, it's not doing what the Boston Dynamics robots are, which is just
no. So it'll be different.
Haul and butt.
And again, I think in one of your videos you talked about the possibility that they could distribute the batteries throughout the system. And hey, why not? It could help with balance and everything else. That way you don't need that giant backpack. Okay, so what we need to do is kind of address this tweet that came out on the 23rd of June that seemed to be referencing a lot about the Teslabot, and everyone thought this was the Teslabot. But when you read the tweet thread a few times, you realize, no, it's not. Right. There's a lot of information in there about it, but you kind of realize that it actually is not. And this was then followed up a couple of weeks later with an actual video from inside of there. And I was rather surprised when I looked at the video to see that it only has about a half Gerber of views, which I thought it should have a lot more. And
I guess we're going to have Gerbers now. So since he uses Gordon.
Yeah. Okay. So if you want to know what a Gerber is, basically when you invite Ross Gerber onto your show, whatever number of views you get, that's the baseline. And if any guest you have after that gets less views than him, you don't invite them back. If they get more, you invite them back. Okay. There you go. And in case Ross is actually listening, I'm back on the show, Ross. So so in this case, I mean, I think he got about 14K on yours. And I'm really surprised. And I encourage people to go take a look at this because they point out a lot of very interesting things. So definitely we'll try to get a link for it in there for you to go ahead and take a look. So we can learn an awful lot. If you look at this, you'll begin to see that, where are the legs? Well, they don't intend to have any legs. That's the whole thing. It's really meant to just be kind of stationary and go up there. And the fact that they don't have legs and stationary means they don't have to worry about batteries. They're going to plug it in. Right. And also all the servos and the controls, everything is down here. There is nothing up there. And we'll get into that a bit more when we start looking at the details of it. Okay. So The next thing we want to talk about is how are humans used in there? Because in that video, he sort of talks about, well, we don't need to make them walk because you don't need humans to necessarily walk in a factory. And it depends on the niche you're going into. He made it very clear that there's a certain niche where the workers are confined to a work area and don't even move around, and others where you have to. So these are examples that might be closer to sort of the manufacturing scenarios that they would be doing it in Tesla. And so, you'll have a worker in this case that is working with a cobot, where the cobot might be doing some sort of pressing or fitting or some sort of other operation like that. And so the worker needs to move around to be able to pick up various parts here and there. Now, this is more typical of an automotive situation where you have the workers that are loading and unloading parts that are then being fed into the robots. Okay, so this starts to look a bit more like feeding the lions at the zoo. You notice the robots are in a cage. And then you have another situation where the worker might have a lift assist if the part is very, very heavy, moving it around. And again, they're fenced off to make sure the workers are protected or the robots are protected, depending on how you want to look at it. And so, these are typically examples where you see human motion is very important. And you notice when they need strength, they had some help. We talked about also these SMT or PCB lines, SMT, surface mounted technology. This is how you produce a lot of the circuit boards that might go into complex equipment like in Starlink. So this is sort of what I was thinking, that if they're not doing this, definitely their sub-suppliers are doing stuff like this when it comes to manufacturing. In that case, the workers were pretty much stationary, except occasionally they had to enter some data. Here's a case where the workers are constantly having to move around the factory to take care of little responsibilities here and there, to make sure some settings are right, maybe pick up something, move it around. But there's still mobility is sort of important in some of these situations. And then we'll begin to see that there's some others where mobility it is maybe not as important, but they still have to turn around to pick up parts that are being fed behind them. So while they're doing a lot of operations in a stationary position, occasionally they have to move around. So do you need something like that, or do you not need something like that? And occasionally you need someone who's able to do quite a lot of walking and moving around. So these are some of the different examples. And the other thing that this kind of points out is that we started out simulating robots and then trying to simulate the factory. And then part of the factory was simulating things like the conveyor systems that were going along there and simulating the mobile robots. Right. And you also had to model the humans. They were kind of important in the whole story of how a factory is being put together. So we've had to go beyond just simulating the robot and simulating everything else that's going on there. And it turns out the kinematics for the human arms are very similar to that of a robot. So once you've sort of mastered for a robot, it's not that hard to go over and apply it to a human.
Right. And this is your software, right?
Yes.
Yeah.
Yes,
so,
it is.
nice.
Yes, it is.
That's
okay.
Very cool. And of course, obviously, it's not just for people who might not know, it's not animation in the sense of like Pixar. This is actually physically.
It's a simulation, right?
It's a simulation of physics, not just for fun animation.
Yes. Yeah. And so you actually have to give specific cycle times to make sure you get an idea how long a particular process is.
Right.
Yeah. The software is Visual Components software. We can put a link in there. We even have a free player that you can find at the App Store. Cool. In Google called Visual Components Experience. You can go on there. It's what we use for our VR as well. So one of the backgrounds I want to give is, how are robots taught today? And, the couple of different ways is they use a process called lead through teach or point by point teaching, where there's a teach pendant. And if you've ever programmed a drone, it's the same idea. If you get this, remote control or some sort, or the joystick that allows the thing to move around, you're doing the same thing, the robot, and teaching different positions, and you're recording position here, then the position here. Let's see. Okay. Like position here, position there, position there. Remember it, and it'll play it back. And that's very tedious and slow, and it's very faithful being able to do that. So if you want to pick up an object, like if I want to pick up this bottle right here, I might teach a point above, go down, grab it, and then say go up. And so I'd have to teach sort of 3 points for it. Well, then you can start having things like programming macros, which are more parametric, where you just say, teach this point at the top of the bottle, and it knows, I need to go above here, go down, go up there. So it seems like it's a bit more intelligent, but it's not AI, trust me. And then there's offline programming, which is doing it more in the virtual world, or rather than using the physical robot to teach it, you jump into this virtual world and do the same thing there. And then,
Okay.
you might say the robots are pretty dumb for the most part. They're just going back to where they've taught back and forth and back and forth. And can they do any variation? And of course, if you start integrating a camera system in, you can make these systems seem far more intelligent than they really are, because now they know, oh, well, the one thing I should say that we don't have now is we don't have task-based. You don't say, oh, the bottle's right there, go grab the bottle.
Right.
It's not, they're not at that stage right now. You've got probably some researchers who've done some voice activation and doing something like that, but in the real world, that's not being done right now. You kind of go over and grab it. Now, so with the camera-based system, you might say the bottle's here, the bottle's there, it's in this orientation, and the robot's got to adapt, it's going to find it. So like one example you would have is something like this, where we're building Legos. So we have these robots that are putting these Legos together, and the Legos are completely randomized coming down this conveyor, and a vision system can come in and pick off what you're looking for. What do you need to build that particular object right now? So that's sort of what you can do with a vision system. And this was done way before you had advanced AI. There was already vision systems that could pick out the locations of parts, the orientations, and figure out what they were and make sure I need a green one now or a red one. I need a 1x4 brick, or I need a 2x8 brick, whatever's going to be needed. So those are examples of what can be done now. Very far.
So this would have been very, very hard coded, like all the little,
yes,
every little brick and all. Yeah, I remember doing stuff like that. It's very complex.
It looks really cool, but yeah, it's being pretty much structured programming and everything else. It's not using AI. Okay, now there's the fun part. What is kinematics? Okay, so kinematics is basically a way to model kinematic linkages. Okay, so we can look at this linkage right here, and you could say that's a robot arm, but that could also be like, the boom mic, right? The mechanism. This could be the microphone over here, and this is the arms coming out. And so you have these linkages that rotate around, and it can be either rotational or they could be translational joints. So it's a way to model kinematic linkages, and basically the links are attached at joints of various degrees of freedom, meaning they might have just a single rotation, or they could have multiple rotations. So if we have something that's like a pin joint, that means it can only rotate in one direction. And you've got examples of pin joints in your house. It's called the hinge on your door. So if you just kind of go to the door, you look at, you've got a hinge mechanism that goes back and forth. And then
you could also think of your elbow.
The elbow is, and we're going to get into that, is the elbow is modeled as a hinge joint, but it's not. You don't have any hinged or pin joints in your body.
Yeah. Oh,
you
well,
model
yes.
You definitely model it that way. I mean, there's other weird stuff going on there, and we take a shortcut and say, just pretend it's modeled that way. Now, when it comes up to your shoulder, that's the closest to actually having something that it's like a ball and socket joint. Right. The way that works. And if you don't know what a ball and socket joint is here, let me just turn this off for a second here, is if you look at this camera, or at this ring light that we have. So we've got a ball and socket. And this actually has 3 degrees of freedom. So your door can only rotate about one axis. This one can rotate forwards and backwards, left and right, and it can rotate this way.
Right.
And the thing about orientation space is you need 3 angles to be able to define what is the orientation of something in space. You also need 3 Cartesian locations to say where it is. So I keep on telling everyone we actually live in a 6-dimensional universe, not a 3-dimensional one, because we have 3 translation and 3 rotation. So that's very important to be able to figure out where something is in space. And that comes up all the time. Okay, so now, usually when we talk about kinematics, we talk about 2 types of kinematics: forward kinematics and inverse kinematics. All right.
This sounds like a lecture that I do on one of my animation classes. So
great. Forward kinematics is basically defined as this: for a given set of robot joint displacements, J1 through Jn, calculate the Cartesian robot tool position, X, Y, Z, and in yaw pitch roll. And of course, we usually know that means like a 4x4 matrix, but the one way to think of it is that position and orientation. And what does that actually mean? So if I do this right, so I've got my arm kind of hanging on out here right now, and I'm saying for a given set of robot displacements, and those displacements can be rotations or translations, which, so I didn't say joint angles.
Right.
because it could be either of those things. And basically what you're saying is I want to know where my fingertip is in space right now. That's my end of tool right there. Or sometimes they call the robot TCP. And so if I move this around like that, I want to know where's that position in space. And we're going to measure with respect to some other frame. So it might be like from my belly button or something like that, which will be the origin. So we'll say, oh, okay, from there, exactly where is it? X, Y, Z. Go ahead and do that. So move your joints. Where is the tip? Now, the inverse kinematics is for a desired Cartesian robot tool position. So now I'm giving the tool position, calculate the required set of joint displacements. So now I want my hand to touch my nose. So it's like, up, you know, and that's where I want to go. So you've got to figure out what are the angles that will get my arm to actually go there and to be able to calculate that.
And just FYI, the inverse kinematics is more computationally complex, obviously.
Oh, yes.
And
yes.
it can also, if you're not careful, lead to things like gimbal lock and stuff where you can actually.
Oh, yeah. Well,
yes.
And we're going to cover, I'm glad you brought that up. That's coming up now. So with forward kinematics, I like to say forward kinematics is basically arithmetic. It's addition, it's addition and multiplication, and that's about it. Inverse kinematics, that's math. There's a lot of math in there. So forward kinematics is very straightforward, very easy to do. And it's pretty much defined as a transform from joint space of your mechanism or your robot to Cartesian space. So we go from joint space to Cartesian space, that's forward. Inverse kinematics is the transform from Cartesian space to joint space. So we're going in the opposite direction. And we're going to look at some examples of forward and inverse kinematics. Or I should say forward and inverse functions. Okay, now, at this point, John, you want to tell your viewers to like and subscribe because the next thing I'm about to mention may cause people to want to leave the video, okay? But please stick around. It's not going to be that bad, okay?
Like and subscribe and then skip the next
Like and subscribe, please. We'll put it in a chapter. You can jump ahead.
There you go.
All right, so here we go. Are you ready? Polar coordinates. Oh, okay. You know,
me and my business partner spent about 2 hours talking about polar coordinates on Thursday. So
yes. Now, for a lot of people, it was like the bane of middle school, polar coordinates. They were absolutely, they didn't understand. We're going to go into it, and trust me, it's not that bad, and it's going to be a good example of how we actually do inverse kinematics. Okay, so polar versus Cartesian coordinates. Now, if you think about what we're trying to do with Cartesian coordinates is define a position in space that you kind of know where it is with respect to something else. So your origin down here. So the way you think of Cartesian coordinates is that as like directions and how to get somewhere. So if I told you where, how do you get to my house? I would say head east 5 blocks or 4 blocks, and then head north 3 blocks. So, basically the instructions are, I'm way back here. Hopefully you can hear me. And I'm saying, walk forward and then turn and then take a few more steps. And now you're here. So that's the way you kind of describe to get to that particular location that you want to have on the Cartesian grid. Now, for polar coordinates, we end up using a radius and an angle to describe the same location in space. And that's theta and r. And what does that mean? I go back to my start location and my origin. And rather than walking straight forward, I end up saying rotate a certain angle like this, and now walk forward. And in this particular case, we know R is going to be 5 because I picked out the Cartesian triple here, right? 3, 4, 5.
I noticed that. I was like, oh, look at you, cleverly making
the angle is something like 38 degrees or something. It's a really hard angle to remember. But it pretty much means that the same point in space can be described 2 different ways. And there are a lot of reasons in physics why you would want to do something in polar coordinates versus Cartesian coordinates, because it's much easier to deal with accelerations and velocities with something that's spinning as opposed to doing it in Cartesian. So it actually makes the math easier. Okay, now.
Well, I mean, if you think about it, just for joints rotate. I mean,
yes.
Unless you're, even if you're walking, everything is all about rotation.
Yes.
There's
a lot of rotation.
Yeah,
And
so it makes a
I'm
lot
gonna-
more sense to deal
right.
with polar coordinates in that case.
Now I'm going to show, I'll show the example. Now, if you remember from polar coordinates, the thing that everyone really didn't like when they took it in middle school math was the transformations between the two. So you first had to learn this, what they call the forward transformation, going from the polar coordinate space, which is the same as like a joint space, into the Cartesian space. So there's this mapping you have to do. And the mapping is just a little bit of trick.
Right.
You look at this triangle here, it's just the radius times the cosine of that angle to get x. And then for y, you just do it over the sine, okay? And then there's the inverse transformation where we have to go the opposite way. We now want to take the x over to there. So say for a given Cartesian location, what's the polar coordinates that I need to describe that same location? And it then becomes this, and it's the arctangent that everyone always had difficulty with. And then this here is like, you can put the square root around this if you want. Basically, the half power means the same thing as the square root. So you calculate the Cartesian distance of r based on that. And
yep, that's probably where everybody gets lost right there, is where they see the inverse tangent. They're like, whoa.
Yes, yes, exactly, exactly. Okay, so okay.
The R on the other hand, by the way, is very straightforward Euclidean distance. That's just
that's very straightforward. And the other thing to point out about forward transformations is they're always a one-to-one transformation. And hopefully we can see this. I don't know if we're in the way. The one-to-one mapping means that for any joint value, there's one and only one Cartesian location that can pop out of it. For the inverse transformation, it's possible that for any Cartesian location, there could be more than one solution to that problem. And I'm going to illustrate that pretty quickly. Here's a simple function, y equals x squared.
Right.
Okay, so if I say x is 2, y is
4. Sorry, I was drinking.
That's okay. It's 4. I was hoping to get a spit take in there, but I guess
there we go.
Okay.
Well, just give me negative 15 or something, and then I'll have to
okay. Oh, we're not going to go down that. Okay. And we know that the inverse x is just equal to square root of y. So if x squared goes to 4, then obviously the square root of 4 is
2. So yeah.
Oh, John.
Sorry. Okay. What did I just
Here we
say?
go. Here we go. All right.
There's a plus and minus. There's a plus and minus.
Just don't. You remember that day in middle school where you took the pop test, where you had memorized everything and you put everything down, and you went skipping home that day because you were so excited that you get 100 on the test for the first time. You told your parents you get 100 on the test. You show up the next day and it's a 50. And why is it a 50? Because you've got to remember that.
Plus or minus.
So the square root of 4 is plus 2 and minus 2. Either one of those works. So there's two possible solutions. And that's what's going on when we look at this equation down here. You've got to remember there's two possible radius. There's a positive radius and a negative radius. And you also can come up with a different angle. You have to throw 180 in the angle as the other possible solution.
But basically from this thing, you'd project it back down the opposite way into the negative XY.
Yes. 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 Yeah. And we're going to show that example. Okay, I guess we're going to go into the singularity first, and then I'm going to show the example.
Give a lot.
Now, the singularity, this is not about black holes, but we're going to explain what a singularity is. And that is,
actually, it
just
is.
kind of go back to this function
Actually, singularities are mathematically defined, so it actually is the singularity.
Yeah, but it is a kind of singularity. And then what I should be saying here is that for the forward transformation, you can say it's for all theta and r. So the forward transformation is not restricted to any value. It works for all values of theta and r. There's no problem that way. Right. The inverse, there are some inputs of the Cartesian where it doesn't work, or you get an ambiguous answer. So it basically it's overall, it's for all x and y, except when x and y is equal to 0. So you need to make sure x and y is not equal to 0. And that has to do with
the reason why is the inverse tangent goes to
the inverse tangent. Okay, yeah. So the inverse tangent is undefined when x and y equals 0. Now, actually, x can be 0. You could say, "Whoa, yeah, you can't have x and you're going to divide by 0." And it's like, don't worry about it. It can actually handle that. What it can't handle is both.
Right.
And the thing is, it doesn't return anything, but the answer is really, it's like anything works.
Right.
Any value of theta will work. So usually when you want to get the origin in polar coordinates, just by definition, they say theta is 0. Well, you could try any theta at all.
Right.
Because all that matters is that r is 0 and it takes care of itself. So it will work for any particular theta. And that means you really have an infinite number of potential solutions at the singularity. Okay. Right. Which begs the question, then why is it called a singularity if there's actually an infinite number?
Right.
To which, when I brought this up in a class, one of my students retorted, because there's no singular solution. So okay, maybe that's true. So that might have been it. And this is basically what a lot of times they refer to gimbal lock, is you get in that situation where two axes align and your math breaks down. So that happens. Okay, let's take a look at the polar robot now. So we've gone through this. And
so if we're doing skipping ahead, this is where the people can come back in and not be scared anymore, right?
Yes, not be scared anymore. Okay.
I'll make sure I put a little chunk in there so people can skip.
Yeah. So now let's stop thinking about polar coordinates. Let's not be scared about polar coordinates, but let's just think about this very simple robot. And the simple robot has an axis here which is able to rotate, and it has another axis out here which is able to translate. And we can see this position right here, which is what we really care about. That's our tool center point.
I swear that looks like a spirograph. You remember those things where you could like draw the cool spirals and stuff?
Yeah. Yes, exactly. And so we're able to move this thing around, and we can look at different values of theta and r that are going to be in here. And so, right now it's at the r is 1000,
right? And
the theta is 0. And so you wouldn't be surprised to find out that the X value up here is 1000 and Y is 0. Okay. Now, quickly in your head, if I said, oh, let's change theta to 45 degrees, what do you think the X and Y values will be?
They should be the same, whatever they are.
They'll be the same. And look at this number, 707. That is the square root of 2 over 2.
Right.
Times 1000, because our radius is 1000. So they're both the same. And basically that's what that is. What you're doing is you're kind of looking at the square root of 2 here.
Right.
So that's where that particular position is. So this is the idea of forward, is I put a number in there and it gives me the Cartesian location and it shows it to me at the same time.
Right.
Now, there's more than one way to get to that position. And that, what I can do is I can show, oh, there's also this other solution here. And that other solution you're looking at, you're like, huh, wait a minute, what's going on there? So there's two possible solutions that we call configurations. And I'll sort of show you what you mean. What I'm going to do is that I want to go to that point. The other way I can get to the point is I can rotate this thing all the way around 180 degrees, and then I can make the movement, the displacement, go negative.
Right.
And of course, it's an absurd solution. It doesn't physically work because in this case, so you would limit it and say, oh, I know mathematically there's two solutions, but we'll just throw out one of them because it's silly.
Right.
Okay, so that's one way of being able to do it. Now, so that's putting in the forward. Now let's do the inverse kinematics. So let's say I want to go to X equals 0 and Y equals 2000. All right. So you would kind of do that in your head and say, oh, okay.
Yeah.
What that means is that X is 0. So this is going to come in all the way here, and the Y is going to go all the way out there. So what that means is I need to get this and probably move it around to 90 degrees, somewhere around there.
Right.
And then take this and slide it out till it's all the way there. And sure enough, if I do that calculation in my head, and I could say, yeah, I want you to go ahead and be 90 degrees here. So I'll go ahead and pop in 90, and then I'll pop in, 2000. And then it's out where I want it to be.
Right.
Okay, so when we do forward kinematics or inverse kinematics, we can actually grab this and we can move it around. And now I can make the computer calculate all these things for me. It's very simple. You just move it, and then it's coming up with the joint values here to match the desired location I want to have. So that's inverse kinematics right there. Okay, now the other thing I'd like to get into is that this is basically what we're doing. So the fundamental concept is what's forward kinematics and inverse kinematics. It's like polar coordinates.
Right.
But when we go to a more complicated mechanism, like a 6-axis robot, it's polar coordinates on steroids. There's a lot more math going on there,
Right.
but fundamentally, that's exactly what's going on. And it's actually not as bad as you think. You know, when you get into it, you begin to realize there's a lot of simple things you can do in certain cases. So, so one thing I want to show is that, you know, here is an example of an articulated robot arm up here. It's very much like a human arm. As a matter of fact, we anthropomorphize it quite a bit by referring to different groups of joints certain ways. So for instance, these joints down here by the base, there's two joints down there. There's one that rotates this way, another one that rotates that way. Those are collectively known as the shoulder joints. Okay. This one up here, which is able to kind of move up and down, surprise, surprise, that's called the elbow.
Right. Yeah.
And then you have three joints out here, which are called the wrist joints. Gotcha. So we get a total of 6 joints that come together here. And what I want to show is, again, this idea of different solutions. So right now, this is what we would say is probably in the primary solution. And you can actually go ahead and flip this around a little bit. So if I go ahead and take this one right now, and I could say, there's another solution right there. Now, I don't know if you saw that. Look at the wrist and look at what just happened there. Whoops, that's not what I want to select. What I want to do is go to there. Do you see how the wrist just kind of changed?
Oh, yeah. Yeah.
Because there's 2 possible solutions there. It's basically you're saying, I can kind of grab it this way and it can go around another way.
Right.
So there's 2 solutions there. And when you actually look at it, what you're going to see is this axis 5 here goes from positive value to a negative value. So it's still the same value, except it changes, and then you get through 180 in there. And then it turns out you can also do stuff like this. You can say, I can have 2 solutions for the elbow. Right. Now that may or may not be possible with your robot. So you may or may not want to do it. We know we can't do it in our arm. You know, our arm, we are not double jointed. Right. We only go one particular way, but it's possible to come up with a robot that is able to go both ways. And then it turns out there's this thing with a shoulder that you basically can come around and one of these things to come over and grab something. So that's what's possible.
Right.
And so now to make it easier to see, I'm running through all the possible solutions. The 8 possible solutions that you have. Now, the reason why there's 8 solutions is 2 shoulder solutions, 2 elbow solutions, and then 2 wrist solutions. And 2 times 2 times 2 is equal to 8. Right. So we see it going through, it's going to the same Cartesian location space every time we have to have. And that's why we say it's a one-to-many kind of mapping. Right. As opposed to a one-to-one. Right. Okay, so that gets us moving along here pretty well. And let me just pause this and put this to sleep right now. So we're done looking at the polar robot. Cool. All right, so how do we actually come up with a model for a human arm? Well, I mean, you kind of look at it. I've got sort of an example here as well. We have the shoulder joints that are in here. So we've modeled it the same way, almost. They take some liberties with some of these, as you would with this type of mannequin. Right. Except we do it mathematically. So this is an example of a jointed model of the robot or of the human arm, where kinematically everything is very, very, very similar. Okay, so what I now would like to do is contrast this. So we'll get the YouTube link in here. This is the description of the giant AI video. And again, so looking at this, we can see, compared to what we were looking at before, okay, the robot's not going to move around. We know the servo drives are down here, but there's lots of questions. It's like, are there motors here? Are there not motors here? How is it kinematically put together? Can we understand something about it? So the other thing I want to point out is that it's not the first time someone has tried to build a humanoid kind of robot to be able to do assembly tasks or do these kind of operations. Back in the early teens, there was a robot called Baxter from Rethink Robotics. Right. And it's a 7 degree of freedom. So that's what I want to get into, is that normally you only need 6 degrees of freedom. We're going to be talking about the 7th degree of freedom a lot here and whether it's going to be there. And the 7th degree of freedom gives you a little bit of redundancy on the elbow, which will be an important thing to look at. But this is like one of the first examples. It's a cobot. The wrists are kind of clunky in that there's no real tooling on there. There's no hand. It's really designed to pick up robot kind of end of arm tooling to be able to do different tasks. It has what's supposed to look like a head with the cameras.
Right.
And just to give you an idea of what it looks like in reality, this is a video we took down at Wayne State. I'm thinking about 8 years ago or so, where we linked it up with the software to show that the movement could be mirrored in our software as you move around. So normally that's how you would teach Baxter. It would be something like that. And then this is the other example that we're actually moving the virtual robot and getting the real one to move along with it.
That's very cool.
So yeah, you can kind of see the little grippers that are in there. And this is not as successful as they were hoping. So it's a real challenge to get something like this that's going to be working right. You see, it's got some funky looking elbows and wrists there that are offset in a very funny manner. So that's an example of the kind of robots that already exist out there. Okay, so now I'm going to go back to the original tweet and look really closely at this, because at first I thought, this is the Tesla robot? Really? So what do we see in here? And we can start to look at the joints to see how the jointed model was put together, the same way we would with this. We kind of looking closely and we can see that this has what appears to be a rotation there and a rotation here. And then it also appears to have a rotation along here. So it looks like I have 3 degrees of freedom right in the shoulder. And so I was trying to do the same thing here, and we can look right there to see where are all the movements.
Right.
One of the first things I did is I looked at the head, and it seems like the head has 2 degrees of freedom.
Okay.
So it can pan tilt, something like that. So yeah, this is pan and this is tilt.
Right.
And it looks like the rotation is right there. Then we go to the shoulder, and the shoulder appears to have 3 axes going through it. It's sometimes a little bit easier to see over here. We know it has a rotation along the horizontal. We have one in here. And then I wasn't sure whether it had a rotation along here. And I think it does, but it's actually this part here that rotates, not the bicep doesn't go. It's more or less the elbow sort of twists along in there. So it looks like there's 3 degrees of freedom. They could correct me if I'm wrong, but that's my guess. Yeah. And then we have along the elbow, we have another sort of pin joint right there. Right. And then it appears that they also have 3 degrees of freedom up here. And this is an interesting choice. So we have this kind of roll that if you take your hand, you would be able to do that. So it's mimicking that pretty well. You also have this pitch like that. And then they also have what would be kind of this yawing motion that you can have in your hand.
Right.
So those are the 3 different ways.
And I assume what you're talking about with the roll is where the discoloration between the 2 different kinds of plastic, the grayer, like the grayer plastic rolls around.
Yes. So this is basically your wrist right here. So this is your wrist. It's not your hand. Your hand starts over here. Right. So don't confuse these axes with anything that's going on in the hand. So the hand is going to be completely separate. Right. We're talking about how we can reorient the hand about what's the center of the wrist. Right. And so this last part, yes, that seems to be what gibbles along there. And of course, we're not built that way. We have this flexure where the whole, everything just sort of twists along there. Where mechanically it's done very different. It's these 2 surfaces that are rotating against each other. Right. And then there seems like the torso has some movement as well. So on the stand, it appears the torso can go back and forth. And it can also lean forward. And so it can lean into things if it needs to. And sometimes you need to do that because by bringing your shoulders further forward, you can extend your reach. Right. You can get out a little bit further.
Cool. Wow.
Okay. So looking a little bit at the hand, up close to sort of figure out what's going on. They were showing a little bit of motion in the video, but not enough that I could kind of figure out what's going on. Looking at the fingers, I think they have different types of fingers, because if you look at these down here, the tips are different than the ones that are there. So some of these seem to have a texture to make it easier to grab certain things. And some of them might be that they're very sensitive to be able to detect something that's going on. So, and now the first thing I wondered is whether these were tendon controlled, the fingers. And the assumption is that they probably had some sort of cabling going through there, because you could sort of see what looks like pulleys in a few places. And we can see like right along here, the elbow, it appears there's some sort of tendon that goes through there. And then sure enough, they confirmed it. They said all these bits down here, I guess are the motors, and they are pulling on those cables.
Right. Oh my gosh. So the tendons go all the way down into the
all the way
substrate. Wow.
down, all the way down.
So just FYI for us people, if you don't pay attention to your anatomy, that's how our fingers work. We don't have any
Yes.
muscles in our hands. Otherwise, our hands would be really, really big. If we had to have all the muscles up here.
Exactly.
So yeah.
And basically everything in our anatomy is working with tendons. But the interesting thing is to think of that, well, the muscle for this thing is like way down here somewhere.
Right.
So that seems to be a lot of cabling going through a lot of places. And I was looking at that, and obviously there's some wires going through there, but around the other side, they must be routing these things.
Right.
And that's a rather interesting design choice, because the thing about cables is that they only work in tension. They're not really going to work in compression. The other thing is they tend to stretch a lot.
Yeah, that's what I was thinking. With that distance, the amount of stretch would be huge.
Yeah. And the other thing is that when you move one arm, all the other cables are also going to bend at the same time.
Yeah.
It's very hard to isolate. So there's going to be coupling. As you move one, it's going to cause all the others to tighten up a little bit more or to loosen, depending on which direction you're going. So there's probably a lot of back drives and everything else going on if you just want to move one particular axis. So it's an interesting design choice. It'd be something probably pretty tricky to come up with a control system, but you never know. The AI may eventually learn how to work that out.
So let me ask you, because the obvious alternative solution would be to put little servos in there, little direct drive servos.
Yeah, exactly. Which is contrasting with the Tesla is going that route. They're putting the servos,
and that's what you can see from that original picture with Optimus, is that they have the small servos in it, right?
Yes.
Yeah.
And we will definitely be getting into a lot of those different servos and how I think they're going to be working. The other thing, one advantage of perhaps using the tendons is you have built-in compliance, and the concern is that people are going to be around this. How do you make sure it doesn't hurt anything? So you get kind of almost a built-in safety in there.
Right.
So
because you're saying that the maximum grip strength is only so much.
Yeah, the strength, or even in the arm, if the arm bumps into something, it's just like, oh, okay, because you get the springiness that's already built into the cable.
Right.
That will allow it to have some sort of built-in compliance, which may be what you want. And again, that's why I encourage everyone to kind of look at the video to understand the design choices and decisions they went through for the particular niche.
Right.
It's not, I wouldn't choose to use the cables, because I remember those little microbots that had that.
Yeah.
One of the first robot in all these little cable drives, or you think like these little crane operators that have these cables are going around.
Right.
It's a challenge, and hey, if they're up for it, why not? So
and this, for people who are not engineers, engineering is always, literally almost the definition of engineering is trade-offs. Yeah, compromise.
Yeah, compromise and trade-offs. Yeah. So it appears that there's some knuckles in here. So we think that the fingers are able to probably grasp like that. It wasn't clear from the video. It looks like the fingers are able to move like this, and then I don't know if there's like one big grasping motion.
Right. Oh yeah, because
we're able to kind of, it's a little tricky, but you can kind of keep some fingers straight and then twist some others, or clench some of them. But it might be that they wanted to have that control and then be able to do this.
Okay.
All right. So, and the other thing that I kind of looked at is the angle that they mounted this onto the body. And they chose about a 15-degree angle, and that's right about, I would have chosen a higher angle than that. And this has to do with what I call, it's actually like a polar singularity, that if you put it on out here and your wrist is right over the center of it, you get kind of the same thing as a gimbal lock.
Right.
And since you want to be able to reach up to higher locations, you're better off having a different angle. So I would have chosen a different angle, and I believe the Tesla is a higher angle. I think it's about 30 degrees.
Interesting.
Which I think is a good choice. And again, this is just a close-up of the elbow that you can sort of see what looks like some sort of pulley here that allows the cabling to go through.
Right. Some sort of conduit. Yeah. So,
Right.
Okay.
Now, in the video, there was a question of like, well, how do you teach the robot, certain tasks? And one of them is that they have what is a puppeteer that is able to put on some VR equipment and pretty much do like an avatar, or for the cult favorite, being John Malkovich, where you actually embody yourself into that robot, and then your movements are then reflected by the robot. And here we can see that they have a tracking on the back because they want to measure the angle of the torso. And they also have something to be able to figure out what the elbow is doing. And then we'll also see there are the hands, and we can still see the elbow trackers here. And then we also have, they're able to do the fingers. So they're trying to teach all the fingers. So from within here with the AR, what he is seeing is the vantage point of the robot.
Yeah.
And then his motions, he's going to look down there, and it's going to feel weird. It's a weird out of body experience. It's like, you know, your hand should be here looking down there, and you're seeing this mechanical hand where you think you should be seeing yours and moving around. And I can talk about that from experience because I've done some similar things, and we're going to jump into that. Is that, you know, also taking like the Vive headset, when you put it on there, it tells you completely where your head is.
Right.
But in my case, just using standard hand trackers, because I haven't found a good data glove that really works well, but this can tell me exactly what my wrist is doing. And then because we want to make ours walk, put these on my feet. So I have these trackers on my feet that will tell me where my feet are. And then one here that, you know, I got here that I'm wearing, whoops, that, you know, sort of the same idea is that you just put that thing on there, and that will tell you exactly where your torso position is. And with that, you can also come up with a human model.
Right.
Okay. So now I don't know what the name is of the robot that they had in there. I don't think they ever mentioned it. You know, the Teslabot is sometimes called Optimus or Optimus subprime. The human models we have in our software are affectionately known as Anna and Otto, which are palindromes.
Oh yeah, there you go.
Yes. Everyone knows what a palindrome is, right?
Just read it backwards and you'll get it.
Yeah, well, I always say it's where Michael Palin of Monty Python keeps his airplane at the palindrome. And then
that is a Monty Python joke.
Right. Then we made a VR version of Anna and Otto that we refer to as Tarsiana. And it stands for the Tracking and Real-Time Control Interface. And Tarsiana just sounded better than like Verana or whatever it was going to be.
Right.
So that's what it is. And besides it, you know, Tarsiana, I think, is like, you know, much nicer name. So.
There you go.
All right. So here we are. This is an example of, I've already gone through walking in the office, and now I'm playing it back and actually using VR to see and record. So this is like a recording, and then I've recorded off the screen by going in again. So it's a little bit meta that you're kind of getting yourself deep inside, but you can see all the tracking that's going on, the rocky push-ups. I wish I was actually that strong.
Yeah, but I was going to say, good for you.
What I'm trying to figure out is, you know, how the elbow is working. What's happening right there is I'm calibrating the chair. When I rotate the physical chair, the real chair ends up right where it's supposed to be. And I'm so confident, even though I can't see the real world, I will sit there because I know that chair is actually there. And the chair is actually, it has its own special inverse kinematics. Every now and then things glitch because the trackers get blocked or something like that. But when you have a really good view, you see, you can get a pretty good human model out of that you would be able to teach with VR.
Right. Okay. And the advantage of this, of course, is number one, you can do it more safely, obviously. Number two, you can do it before the robot's completed. So while the robot's still being constructed. And number three, you can run through, I guess if you'd use AI with this, you can run through thousands or millions of simulations.
Exactly. So there's all kinds of simulations you can do with it. But the main part of this was trying to understand the kinematics of the human model, make sure we had it right, make sure the elbow was working right. Because the problem, if you look at a lot of gaming software where they're trying to do this, you always see these goofy hands or something, or goofy elbows, where the elbow is coming in like this, or the elbow is way up like that. And it's really like, wait, what's the natural way that you want to have the elbow? So I'm doing this without an elbow tracker. That's all being done with inverse kinematics to figure out where the elbow is supposed to be. Because you notice that the elbow doesn't actually go through her body at all. It sort of stays where it's supposed to be. So it's so that's a really important thing to be able to master that and understand it. But this is a 7-degree of freedom arm. And we'll talk in a second the importance of that 7 degrees of freedom.
Very cool. So what happens if what's her name, Tarsiana? If she, let's say you're 6'2" and she's 5'2". Like
rescales.
It does. Okay.
And that's an interesting thing. I was wondering about the other video is that all their robots are the same size,
right?
And whether they picked a certain person who happened to have the right dimensions,
right?
Because you would have to do some sort of mapping. So one of the first things that happens is that when I go into the VR and put my headset on, it measures my height.
Okay.
And from that, it knows exactly how much to scale the body. So she's actually 6'3".
Okay. Oh, so you are that tall. So there you go. So what would happen though? I mean, so let's say we would take this with the real Optimus, who's 5'8", and you can't change the size of that robot because it's a physical object.
Right.
So do you just have to find somebody 5'8" to train it?
No, I don't think you have to. It's really, it's just inverse kinematics. All you really care about is the Cartesian location. There may be a few situations where you're able to grab something that the physical one cannot.
Right.
And then you'd have to say, whoa, wait a minute, I can't do that, or it's going to have to try extra hard to do it. So you want to be pretty close. I think you definitely want to be close.
Okay.
Oh, yeah. So again, just kind of showing how the chairs and everything work.
Right.
Okay, let's get back into the technical details. So that's the background on everything.
Do you want to actually stop this here and let's do like a two-parter? Because I think that's an awful lot of information for our viewers. So we're going to say a quick goodbye. So see you all later. So definitely stay tuned for the next one, because now we're going to talk about Optimus.
See you on the flip side. And
there we go.
I will stop the share. Yep.
Cool. All right. Bye-bye.